Hello, it is a great honor for me to present you some of my results on the uniqueness and non-uniqueness of the positive Z eigenvector for transition probability tensors. This is joint work with Professor Kongqing Chang. So let's begin by asking ourselves, what is a tensor? A tensor is a multilinear mapping, or we can identify that with a hypermatrix, or sometimes multi-dimensional array. Just like in linear algebra, an abstract linear mapping can be identified with a concrete matrix or a two-dimensional array. Tensors naturally arise in algebra, analysis, geometry and topology, physics and engineering, probability, and higher order statistics. The eigenvalues for linear mappings or matrices have been very well understood, and the structures of eigenvalues and eigenvectors are also very well understood. In 2005, Professors Lim and Qi independently introduced two different notions of tensor eigenvalue problems. They are the H eigenvalues and the Z eigenvalues. These two distinct types of eigenvalue problems have since attracted much attention from all areas, or many areas, let's say, of sciences. Just to name a few, here are some notable applications of different types of tensor eigenvalues: best rank 1 approximations, convex approximations or optimizations, spectral hypergraph theory, higher order Markov chains, medical imaging, in particular MRI, multi-relation data mining, quantum entanglement problems, and the nonlinear Klein-Rudman theorem. From matrix eigenvalues to tensor eigenvalues, this is really a quantum leap. So just to lay out the blueprints, some general theory on the eigenvalues and singular values, which is an extension of eigenvalues, to higher order tensors. First is the algebraic geometry approach, and widely using Grübner basis, Bézout theorem, the theory of resultant, and the generalized characteristic polynomials, and also hyperdeterminants. However, from many practical purposes, the main focus is placed on finding real eigenpairs. However, unlike matrices, searching for real eigenpairs is a lot more challenging. One effective way to do so is to use tools from algebraic topology. Here is a quick glance at some algebraic topological methods used in the study of tensor eigenvalue problems: the Brouwer fixed point theorem, the Brouwer degree theory, cohomology theory and fiber bundles, the Lusternik-Schnellmann category theory, and lastly, methods from nonlinear analysis such as genus, contractive mappings, monotone operators, and etc. The Perron-Fabini theorem is a fundamental result in linear algebra and matrix theory, and it is the backbone of page ranking used by Google search. So the desire to extend the Perron-Fabini theorem from the matrix setting to a non-negative tensor setting is highly motivated and have been an ongoing research front for over a decade. I would like to highlight some of the well-established results. Both the existence and the uniqueness of the positive eigenpair remain true for the H eigenvalue problem. The existence of the positive eigenpair remains true for the Z eigenvalue problem. However, quite to the contrary, the uniqueness fails in general. Very few results have been discovered in general about the uniqueness. Surprisingly, we have found some answers in dealing with transition probability or stochastic tensors. So let's begin by recalling some basic definitions and facts involving the Markov chains. A simple definition of a Markov chain is a random process that undergoes transitions from one state to another on a set of values referred to as the state space. The state space is then defined by a transition matrix describing the probabilities of particular transitions and an initial state or initial distribution across the state space. The changes of the state of the system are called transitions. The probabilities associated with various state changes are called transition probabilities. A Markov chain must possess a property that is called the Markov property, which states that the probability distribution of the next state depends only on the current state and not on the sequence of events that lead to it. Stochastic matrices. A stochastic matrix is a matrix used to describe the transitions of a Markov chain. Each of its entries is non-negative, representing a probability. A left, or sometimes people prefer to use right, stochastic matrix is a real square matrix whose every column or row, accordingly, sums to 1. A stochastic vector, or sometimes called a probability vector, is a vector whose elements are non-negative real numbers, also sums to 1. The points, the positions of a probability vector represent the possible outcomes of a discrete random variable, and the vector gives us the probability mass function of that random variable. An initial distribution is given as a column vector. So the desire here is to extend the well-studied Markov chains to higher order Markov chains. A higher order Markov chain is an extension of the finite Markov chain. And in this case, we have to use, instead of a matrix, we have to use a tensor, a higher order tensor. So to create such a tensor, we use this particular summation. And this has now been a well-established notation in the studies. So a tensor here is a non-negative one consisting of n to the m entries of elements ranging from 0 and 1. And it has to satisfy this sum equals 1 condition to qualify to be probability tensor. A stationary probability vector is defined as a distribution that does not change under applications of the transition matrix. So in some respect, to find the stationary point is to find this fixed point of the transition matrix. The Perron-Fabregna theorem ensures that every irreducible stochastic matrix has such a stationary vector, and that the largest absolute value of all eigenvalues is always equal to 1. However, this theorem cannot be applied directly to matrices because to general matrices because they need not be irreducible. And in fact, many of them happen to take on several such eigenvectors. However, for a matrix with strictly positive entries, this vector is unique. So our contribution to extend this line of work to higher order Markov chains or transition probability tensors is based on the work, the pioneer work done by Professors Ng and Wen. Different from their approach, we come up with some other methods, and we end up with several sufficient conditions to ensure the uniqueness of positive Z eigenvector. Here, I will only name 3 different methods used in our paper. One is contraction mappings method. 2 is to use monotone operator method. And 3, we use the Brouwer index of fixed points. Well, I would like to thank you for this wonderful opportunity. And lastly, I would like to quickly go over some of the important literature behind the work we have done. Once again, thank you for your attention.